Time for another draftphysics.com, debatephysics.com video presentation. So another Shitopedia style video, just going over how they really don't have any of the science right and they just don't care. So they've misdescribed the reality and it's just not interesting to them. They won't allow you to even discuss it. So it's not like you can make any edits to their wrongopedia. No, you can't even discuss their wrongopedia, that they're wrong, that they've made a mistake, that they're in error, that they're not really accounting for the truth, and blah, blah, blah. They just won't even discuss it. You cannot disagree with them. What they say is fact, and nothing can challenge their facts. And it's really bad. Okay. I should throw in, Wikipedia, the company, the foundation, has directly stated, that it's all just a legal manipulation. They create this volunteer thing so they don't have to account for any slander or abuse of any human beings. They can just say, well, the volunteers did it, and somehow they can evade legal responsibility for what they're doing. But I don't think the volunteers can. So somebody has to be liable, legally responsible for bullshit and that goes on, shenanigans. And so, these evasions are just kind of funny. So anyway, it would be nice to see that challenged in court, actually. That they can pretend, well, we bought a gang, of thugs and just suggested they should work for us for free. And therefore, we're not responsible for what they do, even though we gave them the guns and we gave them the knives and we gave them the tools to fuck people over. It's not our fault when, yeah, it is your fault. But whatever. That's a subject for a different day. Today is gravity. All right, so the simple contention is that Newton actually argued for gravity that was based on a per second unit, a 1 second. That it would get 9.8 meters of per second velocity, that is velocity per second, in 1 second. And that everything that moved in gravity only added, from the gravitational force, 4.9 meters every 1 second. So gravity only adds 4.9 meters of actual distance per 1 second. So the stuff you get from gravity in the first second is illustrated by you drop something, let's just say in 1 second, a distance that it falls in 1 second. It'll be 5 meters and it'll be going 9.8. So that happens exactly here. If I lift something 4 times as high or even 10 times as high, it doesn't really matter. In the first 4.9 meters, it'll get 10. Let's just say we're going to say the velocity is 10 and the distance is 5, just to simplify things. And so now it's going, 10 meters per second. So gravity doesn't have to act. So if gravity stopped right there, it would end up down here without gravity. It would get these 2 units of distance for free because it's going 10 meters per second. So it's going to collect 5 here and 5 here. And so it's going to end up here if gravity didn't even exist. And then it's this unit, this 4.9 of distance that it's actually going to get from the second. The second is going to just give it this 4.9, and it's going to add 10. It's going to add another 9.8. So you're going to end up with 20 and 20. The distance will be 20 and the velocity will be 20. And here, it's not going to be. See, they're arguing that it's a v squared function and that every one of these units of distance is a unit of force. And that somehow this will end up with 4 units of force because it traveled 4 units of distance. So there's 4x the force here, when clearly it's just 2 units of time. It's only 2 units of 1 second. So it only got 2 units of velocity, and it's clearly indicated by this velocity. It's saying to you it's only 2 units of velocity. There's only 2 units of velocity there. 2 units of time, 2 units of velocity, 2 units of weight. It's only 2 units of energy in the object. That's all it has. It only got 2 seconds of push. It only got 2 of this, every 1 second. So it got 2 seconds worth. That means it got twice that. And that's all it got. This part and this part. That's the part the gravity did. This part was done by the fact that it already had this velocity here. this was for free. So again, half the velocity is here. This is where it's traveling half the velocity. How could it be gaining equal numbers of force in all these locations if it was going half the speed here? They can't be equal amounts per distance. It doesn't make any sense. It's nonsense. 4 of these, okay, is not 4 of these, because this has stopped moving. This isn't moving anymore. So this is just redrop it. I could redrop it again, and then I could redrop it again, and I could redrop it again. Now that's 4 units, but that's going to take 4 seconds. Okay? If I drop it down a staircase, it's not going to take 2 seconds to fall to the bottom of the staircase. It's going to take 4 seconds. It's going to be 4 seconds of gravity, not 2 seconds of gravity. It's going to be 4 seconds worth of force. 4 bangs. Okay? Not just 2 bangs, because it was only 2 seconds worth. Alright. So that's what Newton argued, what gravity is. And they're going to say, or try to say, that Newton said something different, and he didn't say something different than this. Alright, so leave us begin. Should be the gravity page shortly. It should have already been here. Always something. And move it. Whoops, wrong thing. Okay, move this one over. Come on, it'll happen. Alright. I don't know why the text is so big. Well, whatever, it fits close enough. Alright, so so they called this titled Newton's Theory of Gravitation. Main article, Newton's Law of Gravitation. So who knows which one is which? Is this the main article? I don't know. Alright, and then a controversy between Newton and Hooke over the priority. Who gets to say, I figured it out first? And so lots of arguments. Newton hated Hooke and blah, blah, blah. Who cares? In 1657, Robert Hooke published his Micrographia, in which he hypothesized that the moon must have its own gravity, which is sort of interesting, but yes, okay. Yes, of course, it's a fact that all the matter has the gravity, so that's the interesting fact. All right, in 1666, kind of a scary year, he added 2 further principles: that all bodies move in straight lines until deflected by some force, and that the affecting force is stronger for closer bodies. So the fact that everything moves in a straight line is a nice statement that physics doesn't pay any attention to anymore. Obviously, photons are doing all kinds of waving. Anyway, in communication to the Royal Society in Hooke wrote, so this is a communication to them. I guess he didn't present this in person, but anyway. I will explain a system of the world very different from any yet received. It is founded on the following positions. 1, that all the heavenly bodies have not only a gravitation of their parts to their own proper center, but that they also mutually affect each other within their spheres of action. So he might be saying that the pieces of the body are also gravitationally attracted to the other pieces of the body. That all bodies having a... So the thing to say is that all matter produces this effect. Now the question is what causes the effect? And obviously my simple argument is they couldn't know about electrons and protons yet. Hadn't really nailed down charge and all that kind of stuff. But the idea that there was something small inside of material things, and that stuff would move, and that you could understand the consequence of movement would have to be using energy, that something doesn't move for no reason. So everything that moves for a reason. There's a cause. Now if you're causing something to move that's heavier than the thing moving it, then you can figure out that it's not going to go as fast, and that would be a reason to understand that all motion consumes force, and that the consumption of force would be the cause of gravity. Alright, that all bodies having a simple motion will continue to move in a straight line unless continually deflected from it by some extraneous force. So I like that he say continually, so that's the key point, is that the force can't just hit something and it goes. The force has to continue to push something. It sticks to something. It is consumed by the something until the something releases it. And so motion is using force. It is not just exchanged from the field, the force, to the object. The force is contained by the object. The object possesses the force, causing them to describe a circle, an ellipse, or some other curve. So he's just talking now about why things orbit. That is, attraction is so much the greater as the bodies are nearer. So this is the inverse square law, And I can, it's the sun for, light does exactly the same law. So I'm just saying the fact that everybody knew about light already, and that, light gets brighter, 4 times brighter for twice the distance. You get closer by twice the distance, you get hit by twice as many photons. So this idea already existed, and you're just talking about reversing the photons. You're just saying, well, what if the photons moved in the opposite direction? Well, yeah, that would behave just like gravity. All right. So to me, this is not a very big stumbling block for physicists to argue with each other over. But at that time, maybe it's a bigger deal, okay? But I just mean, the very fact that they don't compare it to all the other things that obey the inverse square law, I guess, is the funny part for me, like a spray of water or, an atomizer. All kinds of things are going to do exactly the same thing as the inverse square law. So why wouldn't you just say gravity is doing what all these other things that come, that radiate from a point in all directions, they're all doing the same thing. An explosion of a piece of dynamite would be exactly the same thing. Inverse square law to how much damage it's going to do to you. A nuclear bomb, inverse square law. They all have an inverse square. They all obey an inverse square law. It's like universal for anything that releases energy in all possible directions. As to the proportion in which these forces diminish by an increase in distance, I have not discovered it. So that was in 1666. Newton published in 1668, so clearly Newton did discover it. But anyway, all right. So Hooke's 1674, no, that's right, it was 86. So sorry, it wasn't 3 years later, it was 86 that Newton published, right? Yeah, something like that. All right, Hooke's 1674, Grasham lecture, an attempt to prove the annual motion of the Earth explained gravitation applied to all celestial bodies. Okay, so that's a redundancy. All right, so in 1684, Newton sent a manuscript to Edmund Halley titled some kind of Latin crap on the motion of bodies in an orbit, which provided a physical justification for Kepler's law of planetary motion. Halley was impressed by the manuscript and urged Newton to expand on it. So that's why Newton wrote the Principia, is essentially because he was encouraged to. And a few years later, Newton published the groundbreaking book called Philosophia de Naturalis Principia de Mathematica, or whatever. Principia, I guess it is. I don't know. Mathematical Principles of Natural Philosophy. Okay, well, who cares about that crap? And frankly, I think he should have called it something like Geometrical Principles, because it's not really about the math, it's about the geometry. I mean, the whole book is just geometry. All right, in his book, Newton described gravitation, so we're finally getting to the subject of gravity. Wow, it took a while. As a universal force, and claimed that the force which keeps the planets and their orbs must be reciprocally as the squares of their distance from the centers about which they revolve. So it's just basically saying it works just like photons. Whatever this gravity stuff is, it's doing exactly the same thing as photons. There's this little stuff moving. You could just argue the stuff gets denser and denser because you're confining the amount of space that the stuff is in. So the inverse square just means this. As you go out, you spread in 2 directions, right? So you're spreading this way, height, and you're spreading widthwise. So you're going in this direction, you're using up this dimension. And in the other 2 dimensions, you're spreading the material this way, and you're spreading the material that way. That's why it's an R squared. It would just be if it was only spreading in one way, it would just be an R rule. It's an R squared rule because the area of the square is 4 times the sides. Okay. In the book, Newton described, okay, blah, 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 we did that. All right. In his book, Newton described gravitation as universal, claimed that the forces which keep planets must be, okay, we already did all that, right? This statement was later condensed into the following inverse square law. Okay, so later condensed. Now, I still have some argument about whether you need to multiply the masses. Now, the reason why you would multiply the masses is the two forces, like one body is creating its own gravity, this body is creating its own gravity, and the fact is they're adding in the sense that you're multiplying them by having them go in opposite directions. That's this, so it's magnifying it by the fact that they're in opposite directions. Okay, so that's probably the justification for the multiplication there. All right, so he came up with the idea that there's a gravitational constant, and the gravitational constant is what's going to dictate the output. Okay, so anyway, where F is the force, M1 or 2 are the masses of the object interacting, R is the distance between the center of the masses, and G is the gravitational constant, 6.674, which he didn't have then. Okay, he just had a constant. He didn't know what it was. Newton's principle was well received by the scientific community, and his law of gravitation quickly spread across the European world. More than a century later, in 1821, his theory of gravitation rose to even greater prominence when it was used to predict the existence of Neptune. So it's just this idea that you can perfectly trace the motions of everything in the solar system based on their direction and velocity, and you can just basically predict where they'll be 10 years from now because the laws of all the tugs between all the bodies is relatively consistent. And it's the very fact that the planets do affect each other that means that anything that changes a little bit, where it moves a little too much or it moves a little too little, you know that something must have perturbated it, something must have affected it, and that's why they predicted Neptune, because they knew something was screwing up the orbit of Uranus. Okay. Use the theory to create a table modeling the orbit of Uranus, which was shown to differ slightly from the planet's actual trajectory. In order to explain this discrepancy, so this really is nothing about Newton. I mean, frankly, or the fact that Newton tells you that it's 9.8 meters per 1 second, as Galileo said. Many astronomers speculated that there might be a large object beyond the orbit of Uranus, which was determined, 1846. So this is the Newton page, and they're talking about 1846. All right, the astronomers John Adams and Lee independently said Newton's law to predict Neptune's location in the night sky, and the planet was discovered there within a day. Okay, so that was all they did for Newton. So even though Newton's gravitational theory is the thing he's most noted for, this is how they described Newton's theory, by telling us what Hooke said and barely saying anything about what Newton said, and then talking about what people did in the 18 and 1900s. I mean, what a pile of nothing. Well, the 1800s. So that's really disappointing. So they really haven't gotten to the 9.8 meters per second squared thing, right? So we still don't have anybody saying 9.8 meters per second squared. And that's the big piece of crap that they all spout. They all spout it as 9.8 meters per second squared, but we don't have that anywhere in this document yet. All right, even though it is 9.8 meters per 1 second is what Newton theorized. Okay. All right, so I don't know, do I want to do general relativity? I mean, it's just so irrelevant to the subject of gravity, right? And it's certainly not going to settle the Newtonian argument about whether it's per second or per seconds, any number of seconds. You can't say 9.8 meters per second squared because there's just it doesn't make any sense. You can't square 1 and get anywhere. It's 9.8 meters per 1 second. If you make it 2 seconds, or you make it 1.5 seconds, or you make it some other number of seconds, then you have to change the 9.8. It's 19.6 per 2 seconds, and it's 4.8 per 1/2 second. So if I change the number of seconds, I have to change the 9.8. It's not 9.8 per second squared. It's 9.8 per 1 second. That's what this thing should say, is solve that controversy. All right, so I guess we have to read this. Eventually, astronomers noticed an eccentric. So they're going to talk about goddamn Mercury again. All right, so this is all just the Mercury thing. Finally, in 1915, Albert Einstein developed a theory of general relativity which was able to accurately model Mercury's orbit. So his 1905 paper, suggesting the theory, certainly didn't explain anything. It didn't have any math to shove on top of it. So it was 10 years later when he published the math, the convoluted, insanely convoluted math, by the way. You're not going to find a video where they actually solve Einstein's equation. I've looked for them. You can't find one where they actually put real numbers in and actually solve it and show how it perfectly predicted Mercury's orbit. In general relativity, the effects of gravitation are ascribed to space-time curvature instead of a force. So even though, Hooke pointed out it behaves just like a force in the sense he's saying it's inverse square law, so it matches a fire hose and it matches lots of things where the force is spread in 2 dimensions. Certainly matches sunlight perfectly. So it matches the radiation coming off the sun perfectly. You just reverse it and it's exactly the same force. If the light photons were going in the opposite direction into the sun, it would look just like gravity. It would appear to be just exactly like gravity. And it's exactly how they teach relativity in college. So Leonard Susskind will use fluid as a way of illustrating the flow of gravity. So it's ironic that they talk about this curvature, and yet the curvature is really completely duplicated by bits of force moving towards the center of objects. Just like they radiate out from the center of objects. And the simple truth is, if some other object is radiating on you, from all sides, then it's going to look like it's the energy's coming from around the universe and all focused on you. If I put anything in a field of pressure, it's going to look from the thing sitting in the field of pressure, it's going to look like everything in the universe is out to get it. It's all going to come into it as if there's this equal amount of stuff all headed just for me. The light hitting me now is all photons that are hitting right for me. I can't see the ones that don't hit me. I can't be affected by the ones that don't hit me. And all the ones hitting me looks like I'm being surrounded by the force. All right. Just silly. Einstein began to toy with this idea in the form of equivalence principle, which Newton's bucket blows out of the water, essentially. So I guess we'll do Newton's bucket. I'll have to make a note to do that. I have to make a 5-minute video on that. I'll have to make a short on that one even. Maybe you can make a short. A discovery which he later described as the happiest thought of my life, which is just so silly. Because the fact is, gravity is such a different force. You can't compare it to an elevator because, frankly, an elevator is pushing you from your feet up. The pressure has to go through your whole body and be interpreted by your whole body. Gravity moves every single one of your atoms. It moves everything. That's why you don't feel it. Gravity, you can't feel gravity because it's not moving the end of your finger different than the middle of your finger, then your elbow, then your eye. No parts of your body are moving unevenly. They're all falling at the same exact rate. They're all being pushed at the same exact rate. So you can't feel unevenness. Where when you're standing on the ground pushing you up is pushing you really uneven. The ground's not pushing all of your atoms, so gravity pushes all of your atoms evenly. The ground pushes back by just pushing on your feet or your ass, depending on what part of you is sticking to the ground. And so they're completely different. They're not equivalent forces. One of them's acting so much differently than the other one. One's a nuclear force and one is a chemical force. All right. Einstein began to toy with the idea in the form of equivalence principle, which, in this theory, free fall is considered to be equivalent to inertial motion. So it's obviously, there's no point in calling something inertial motion. I mean, mass motion. I mean, it doesn't mean anything. meaning that free fall inertial objects are accelerated relative to non-inertial observers on the ground. So you're not falling relative to something, you're falling, period. You either have force pushing you or you don't have force pushing you. So this is a clear distinction between Newton and Einstein, because clearly Newton argued that space, positions in space, are real things. They're solid things. They don't go anywhere. Solid in terms of as concept. A place in space is a place in space, and the stuff moves by the place in space. So stuff can sit in that place in space, but everything is moving relative to fixed places in space. And this is obviously quite an opposite perception. Okay. In contrast to Newton's physics, Einstein believed that it was possible for this acceleration to occur without any force being applied to the object. So obviously that is absolutely silly. And I would argue, Newton would argue, you're not going to move anything without applying a force. Everything acquires a velocity from a force. They do not acquire velocity because nothing happened. Something has to happen, and the bent geodesic isn't a thing. A mathematical concept is not what moves stuff in gravity. What moves stuff in gravity is that gravity is a real force, just like photons are a real force. That's why it moves the same speed. So all this stuff moves the same speed. Electric, magnetic, gravity, light, all moves the same speed, the speed of force, frankly. That's what it should be called. Not the speed of light, the speed of force. Even that logic escapes these people, these frickin' scientists. All right. Anyway, Einstein proposed that space-time is curved by matter. So somehow matter exists in an ether, right? Some kind of goop called space-time, because it's affecting the space-time. So space-time must be a something, because you can't affect a nothing. So it must be a something, and somehow matter's affecting it. And that free-falling objects are moving along locally straight paths in curved space-time. So obviously he's saying somehow you're moving into an object and there's no curvature necessary, right? I mean, rays of light don't curve. They're not curving out of the sun. They're going in direct straight lines. And he's saying because the density or the magnitude or the number of those lines increases, so as you get close, if you have rays of light coming out, they're far away from each other out here, but they get closer and closer as they move in here. And so he's saying the density of those lines, you could say, or ray lines, is somehow understood by the matter. Somehow the matter knows that it's in a place where the lines are closer together. But there's no real lines. There's just this idea that somehow they know they're in a place where the force that doesn't exist is stronger. I mean, it doesn't make any sense. All right. These straight paths are called geodesics, as in Newton's first law of motion. Yeah, I don't know if that's his first law, but anyway, Einstein believed that the force applied to an object would cause it to deviate from a geodesic. For instance, people standing on the surface of the Earth are prevented from following a geodesic path because the mechanical resistance of the Earth exerts an upward force on them. So again, what's geodesic about it? It's clearly straight line force. And yes, there's some force hitting me from this side, and there's force hitting me from this side. There's actually force hitting me directly horizontal, but that's equal force. The same amount is pushing me this way as pushing me that way, so I don't move in those directions. And these directions just cancel each other. It pushes me a little sideways, the other side pushes me back this way, so they all cancel. And so all you have is the differential in the total number of lines hitting me from the top versus lines coming from the bottom. And that's the deficit we fall into. All right. I mean, just, it's so bad. Path, because the mechanical resistance exerts upward force on them. This explains why moving along a geodesic in space-time is considered inertial. So it doesn't explain it to me, and it doesn't explain what the hell an inertial is. You should have a hyperlink on all the inertials. Oh, God. Okay, anyway. Einstein's description of gravity was quickly accepted by the majority of physicists. Now, it wasn't, so that's a lie, right? So we know that most physicists said, what the fuck is he talking about? And it wasn't until Eddington in 1919 provided a piece of credible evidence. And again, it was incredible evidence because in Eddington's journal, he admitted the data was 10% of what he was hoping for. And he actually said, I wouldn't stake my life on these results. Obviously, with 10% of the data quality, you're not going to feel very good about doing a scientific experiment with 10% of the data quality. So it's a pretty bad experiment. And it wasn't until then that this crap was accepted. So it's just grotesquely incorrect. For 20 years, the subject was barely a murmur among physicists. And it wasn't until the big proving light bent twice as much by gravity, which wasn't, again, as I explained in the other video, that Einstein 2 years earlier thought it was just one time. So if they would have done the eclipse experiment 2 years earlier, Einstein would have been proven wrong, as it was able to explain a wide variety of previously baffling experimental results. So again, where did it do any of that? So that's just talk, right? What's the reference? Brush. Why was relativity accepted? So it wasn't, we already know the answer to that question. It was accepted because of Eddington, nothing else. All right. In the coming years, a wide range of experiments provided additional support for the idea of general relativity, all just circumstantial mush. So the fact that atomic clocks are broken when you give them velocity. So atomic clocks can be easily broken just by adding more isotopes. So if I put the little atomic isotopes closer to each other, their half-life changes. So something could have an atom could have a 10,000 year half-life, but if I put it with a whole bunch of others, then its half-life turns into 6 days. So yes, you can break atomic clocks, and velocity just happens to break atomic clocks. Today, Einstein's theory of relativity is used for all gravitational calculations where absolute precision is desired. So it's really not used anywhere, and so that's just talk again. So they're not really going to show any place where anybody's using explicit Einstein mathematics, and that most of it is just approximations, and that's good enough. And so they're just playing a game that there's any precision to this whole theory, because there isn't. Although Newton's inverse square law continues to be useful and fairly accurate approximation. So it's not an approximation. It's like saying the sun only approximates the inverse square law. No, it doesn't just approximate it. It duplicates it quite perfectly over any reasonable length of time. So yes, obviously when there's a sunspot, there's more energy going where the sunspot is. But the overall pattern of its function is perfectly within the confinement of accurately described by the inverse square law. And gravity is the same way. You can have fluctuations in gravity based on frickin' earthquakes. All kinds of things can change a little bit of the gravity for a millisecond or two. So just absolute crap. So they really have dissed the whole subject of gravity here, because they're really not talking about the most fundamental element of gravity, which is the 9.8 meters per second that we experience. Just totally ignored. All right, modern physics, general relativity remains a framework for understanding of gravity. General relativity, while some scientists have speculated that general relativity may not be applicable at all in certain scenarios, like in reality, it doesn't work. Yeah, so, I mean, it's just, you don't need to know any more than inverse square law and the gravitational constant. Those two things will tell you all you need to know about what's going to happen to anything in any kind of circumstance. And the only thing that can be hidden from you is some detail like, well, what if the center of the earth is precessing? What if the sun was actually inside the center of the sun? There were two things rotating. What if there was a binary core in the center of the sun? Right? We can't see it. We can't say for sure. We know the sun does rotate now, so we do know that the inside of the sun is just rotating. So what if it does have a binary component in its core? Clearly, we'd have to calculate that change in the gravity that constantly is happening when things go from here to here, from here to here. There's a little change in the amount of gravity. And a little dilution of that inverse square law because the center of the gravity is flexible. So yeah, but that's true. But we're not talking about special circumstances. We're not talking about details that fine. So they really just diss the whole subject here. So Einstein's field equations, that will not be much fun. So I think we will pass on that. Gravity and quantum mechanics. Oh, I don't know if that's worth it either. Tests for general relativity. All the tests have to do with atomic clocks, so it's really kind of a useless pile of mush. And, why haven't they done the Eddington experiment from space is the big question, right? Why not prove this bullshit, of light being twice as bent by gravity by actually just doing the Eddington experiment from a satellite? 400 times better resolution. The experiment is a breeze. It's so easy to do from space, and we're supposed to believe they've never even tried it, which is idiotic. All right, Earth's gravity. Well, that might be a better subject, but maybe I'll save it for the next time, frankly. Well, maybe I'll take a pause, and then I'll decide whether I want to do that. Yeah, that's what I'll do. I'll pause. All right, so leave us do this. Okay, Earth's gravity. Main article, gravity of Earth. I don't know is that the same page as this? Oh, no, it's a different page. Okay, well, maybe we'll go to that. Every planetary body, including the Earth, is surrounded by its own gravitational field, which can be conceptualized with Newtonian physics as exerting an attractive force on all objects. So every object creates a deficit on its surface. So there's always more energy that goes in than it comes out. All right, it would be, I think, the simple way of saying it. Assuming that a spherical symmetrical planet with the strength of the field at a given point above the surface is proportional to the planetary body's mass and inversely proportional to the square of the distance from the center of the body. So again, just repeating what they've already talked about. So the fact is it's based on this gravitational constant will decide how much it moves. Now this animation is basically showing the little thing moves a lot, the big thing doesn't move much at all, because yes, the big thing has to be affected by a small amount of change in the environment, and the big thing is creating a big amount of change for the little thing's environment. And that's the way to look at it. So the amount of force that's changing for the big thing is small, and the amount of force that's hitting the little thing, the change in the force, is big. Okay, so if these objects weren't here, the objects would stay where they are because the field of force hasn't been changed any, kind of obviously. And they're just being pushed together because both of them are essentially absorbing force coming from the outside. So all the force coming from the outside, a little bit of it is being absorbed and therefore isn't getting to this surface. And the big thing is blocking it from getting to this surface. And that blocking is what's causing the objects to crash into each other. It's clearly just a photonic type force, and it's clearly just shadowing. So it's Lesage gravity, essentially, okay, with the added understanding that drag really does happen to electrons and protons. All right, so, and then it says here, if the two objects were the same size, it doesn't say that, that's what it should say, then obviously you'd see them both move the same amount, because they would be affecting each other's environment the same amount. So it's just about how your gravity affects something else versus how much the something else affects you. So you can understand the Earth is gigantic, it's affecting your environment a lot, and you're not even affecting the Earth's environment barely at all because you're too small to affect it. You can't create enough of a shadow. All right, the strength of the gravitational field is numerically equal to the acceleration of the objects under its influence. So whatever the hell that means, okay. The acceleration is equal to the acceleration, numerically. The rate of acceleration of a falling object near Earth's surface varies very slightly depending on latitude. So again, this is a bit of minutia. You're just saying there are places on Earth where there is more mass, or the mass is denser atoms. So if there's a place in the Earth where there's a whole bunch of heavier atoms, then there's going to be more gravity there, because it's the number of atoms, the amount of electrons and protons, that decide how much gravity there's going to be. All right, the surface features such as mountains and ridges and perhaps unusually high or low subsurface densities for purpose of weights and measures, a standard gravity value is defined by the International Bureau of Weights and Measures International System of Units. Too bad they don't give you that. But the other interesting fact is if motion is the cause of gravity, then also things that are hotter would be producing a little bit more gravity. All right. But no one's done that experiment. The force of gravity on Earth is the result of vector sum of two forces. So they're basically just saying, yes, the force you're applying to the Earth, which is so minute it's not even worth talking about, versus the gigantic change in the environment the Earth is creating for you. The stuff coming from down there has to go through the entire 1,000 miles of the Earth to get to me. And in that voyage, it's lost a little of its mojo. And so there's more stuff hitting me down than is hitting me going back up. And that's just the simple truth. And that's why I move into the Earth and penetrate it. And then the Earth, because it's pressurized, pushes me back. All right, so I have momentum constantly moving down, constantly moving up, constantly moving down, constantly moving down, up. I'm creating gravity because my mass is moving. I create gravity in one direction, and then I create gravity in the other direction. Yeah. All right. The gravitational attraction in accordance with Newton's universal law of gravitational, and B, the centrifugal force. So there's no centrifugal force. Any rotational force is really vectors just trying to escape, and they're being forced by gravity, okay, to not escape. All right, which results from the choice of an earthbound rotating frame of reference. Some more bullshit about these fake notions of frames, which again is completely anti-Newtonian, so they don't even provide the Newtonian retort to this, which would be, it don't happen that way. The force of gravity is weakest at the equator because of the centrifugal force causes the Earth's rotation, and because points on the equator are further from the center of the Earth. So the fact is the matter is less dense because it's been spread out. So it's pushed out further because it has a higher speed. So essentially every piece of the Earth is actually rotating around the center of the Earth. It's all little satellites. We're satellites. All right, and we have a velocity, and the satellite has a velocity, and we have to be pulled down by the gravitational force more than our velocity away, so we can't escape, and so we just keep doing that. And so the stuff on the equator has moved out because it's moving a little faster. Its rotational speed is a little higher because it's further away from the center. So the rotational speed is causing a pressure that's causing things to be able to have more velocity, which means they want to escape, and the gravity isn't quite strong enough to push them in enough. So they're out further, so it's less dense. So that all the matter, if you drill a hole at the equator, it's easier to drill the hole because the matter isn't as pressurized, you could argue. All right, anyway, the force of gravity is weakest at the equator and caused by the Earth's rotation because points on the equator are furthest from the center of the Earth and therefore rotating faster, I should say. The force of gravity varies with latitude and increases from about 9.7 to 9.7.80 meters per second squared. There's no squared seconds. It's 9.8 meters per 1 second. That's the rate that gravity imposes velocity. It does not impose 9.7 per any number of seconds squared. It's not any number of seconds squared. That's inaccurate. It's 1 second. Okay, and obviously there'd be no point in squaring 1 second. All right, at the equator to about 9.832 meters per second squared at the poles. So this meters per second squared thing, there's no rational reason they put this second squared here. It's not rational. It's not a proper ratio. It is not 9.8 meters per second of velocity per anything other than 1 unit of 1 second of time. All right. Origin. I don't know. It's not much of an origin paragraph. The earliest gravity, whatever that means, possibly in the form of quantum gravity. Oh, sorry. The earliest gravity, possibly in the form of quantum gravity, supergravity, or gravitational singularity, along with ordinary space and time, developed during the Planck epoch. So this is where they're saying the origin of gravity. The bent geodesic they have a creation date for the bent geodesic. Isn't that amazing? I mean, this is all just made up, possibly in the form of primeval states such as false vacuum, quantum vacuum, virtual particle in a currently unknown manner. I mean, what a big pile of mush this is. Why even print this crap? This is just them saying something like, Feynman liked gremlins. It was his favorite imaginary pet. So why don't we just say gremlins did it? I mean, it's just so bad. Okay, so gravitational radiation. I mean, why would they? Oh, gravitational waves, the big fake LIGO crap. So they throw that into this fucking subject. The speed of gravity, well, at least that is consistent with it being the speed of force. So at least they know that part. But again, they're depending on LIGO to tell them that truth too. Oh, brother. Alright, so now we got all kinds of weird crap and historical alternative theories. Yeah, so at least Lesage is mentioned, so they got a page on that, I imagine, and so been there, will do that. And that's all you really need. I mean, Whitehead, oh dear, that's got to be pretty scary. So I wonder why Whitehead is mentioned. Why is Whitehead's theory of gravitation a thing? Why does it deserve a mention? I mean, religious nuts, essentially. Spiritualists. Why do we have to have the theories of the spiritualists? Alright, so then a whole bunch of references, and then we have a whole bunch of and then we have the real references. So we have a bunch of references, and then we have real references and just partial references. So, modern alternative theories. I wonder what you have to do to get on this list. So, they have a whole bunch of stuff here. I'm sure they're not going to say 2 plus 2 plus 2 plus 2 physics. It's not going to get a fair mention. So I wonder why these get fair mention and those don't, whatever those are. All right. Well, anyway, enough of a video and such. So, so we'll just keep hitting buttons and going to different subjects. It's all bad science. It's all bad. It's just bad science. You don't do science this way. You tell us what happens. You show us, in a sense, that there's experiments that do this certain thing, and what do you think this certain outcome means? I mean, the outcome for gravity is as I described it. It's just explicitly the truth. All right, the units of gravity, you don't get units of gravity per unit of distance. You get units of gravity per units of time. And it's just really undisputable. There's no rational counter-argument to the fact that it's a time-dependent force. Time dependency, if understood and obeyed, works perfectly. All right. So anyway, till the next time and such and so forth and whatnot. I can only do my part. I mean, I can't help it if you're stupid poo eaters. I mean, if that's what you want to do, you want to eat the poo, what am I going to do? I can hit you with a stick, but it doesn't seem to work. Yeah. So, go ahead. Embarrass yourselves. What can I do? I can't do anything to stop you. I'll just do my part and show you the better road. You don't want to take it? That's your problem.